In the previous lessons, we have dealt with various topics of research methodology. We have taken up research problem, research design, questionnaire making, sampling design, but now it's time to go for the analysis part that is to be done in research methodology. And for this, we need some mathematical concepts which we are taking in this lesson. So, this lesson will be a short tour to some mathematical grounds which are used while performing the analysis of a questionnaire. So, the topics that we'll be taking up in this lesson are measures of central tendency, then we'll be taking up measures of dispersion. In that, we'll be taking up range, quartile deviation, mean deviation, standard deviation. After considering these measures of dispersion, we'll move on to normal distribution. Normal distribution is one of the most used distribution for analysis. Then we will look onto the concepts of skewness and kurtosis along with their pictorial representation. After that, we'll be taking up the standardization of data concept, how to standardize data via normal distribution. Then we'll move on to two variable concepts, that is correlation and regression. After that, we'll be moving on to the chi-square analysis part. We'll be taking up the application, how chi-square works, what are the limitations of chi-square distribution, what are the steps involved in chi-square distribution. And then with the chi-square distribution, we'll be moving on to ANOVA, that is analysis of variance topic, wherein we'll be taking up the calculation of F ratio, stating the assumptions of ANOVA, what are the ANOVA types, and then we'll be touching a little bit of topic of ANCOVA. So with these concerns and topics, we'll take up how to analyze data mathematically. So let's begin with the first mathematical measure, that is measure of central tendency. A measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within that set of data. As such, measures of central tendency are sometimes called as measures of central location. They are also classed as summary statistics. The mean, which is often called as average, is most likely the measure of central tendency that we take up in various analyses. But apart from mean, there is median and mode, which are taken as measures of central tendency. The mean, median, and mode are all valid measures of central tendency, but under different conditions. Some measures of central tendency become more appropriate to use than others. In the following section, we'll take a look at where mean, median, and mode can be used, and then how to calculate them and under what conditions they will be taken up. So, the very first measure is mean, which is most widely used in various applications. Mean, or popularly known as arithmetic mean, is the sum of the observations divided by the number of the observations. It can be used for both discrete and continuous data, although it is more often used for continuous data. But mean has one major disadvantage, that is, it is susceptible to the influence of outliers. So if there is an extreme value in your data set, then the mean is affected by that extreme value. Median, which is also called as positional average, is the middle score for a set of data that has been arranged in the order of magnitude. The advantage of median is that it is less affected by the outliers and is therefore used for skewed data. Mode is the value which occurs most frequently in a set of observations and around which the other items of these sets cluster densely. Mode is used widely for categorical data where we wish to know which is the most common category. So, if we have a nominal data, that is a categorical data, then we prefer taking mode. If we have ordinal data, then we go with median. If we have ratio data or interval data, which is not skewed, then we go with the mean. Then we go with mean. And if we have interval or ratio data which is skewed, then we go for median. Because median is the one which is not affected by the outliers, so it can be used for skewed data, whereas mean is affected by the outliers, so we prefer taking up to those data where there is symmetricity. Now, before moving on, let's have a quick understanding on how to find out the values of mean, median, mode for discrete figures, and then we'll be taking up SPSS software and we'll be seeing how SPSS software easily gives these three values just on a click away. Suppose this is your data set and we want to find mean, median, mode, then SPSS directly gives its calculations. We'll just go for descriptive stats, then we'll go with descriptives. Data is a variable that we need to take into account. Then we'll go with options. For the time being, let us take mean only. We'll take up standard deviation, minimum, maximum later on. Continue. Okay. So it is simply giving that this data constitutes 40 observations, and of those 40 observations, the mean is coming out to be 1.7586. Then we can go to frequency. This will show frequency table. Here we can go with mean, median, mode, all the three. We'll take up other measures also later on. Then let us have so this is the data set analysis. They are saying that there are 40 values, there is no missing value. Then the mean of the data set is coming out to be 1.7586. Median is coming out to be 1.76. Modal value, that is frequently occurring value, is 1.76. But it is showing that our data set is not unimodal, it is multimodal. So this way we can compute mean, median, mode. And as far as the formulas are concerned, so we have mean is simply the sum of observations divided by total number of observations. Median is the middle value. So if my data is odd data, then it is simply n plus 1 by 2th observation after arranging the data into ascending or descending order. And if it's even data, then it's the average of nth and n plus 1th observation. Then mode is the maximum frequency that is occurring in the data set. So this is the way by which we calculate mean, median, mode. Apart from these central tendencies, we have geometric mean, harmonic mean, etc. But they are not widely used. The most widely used central tendency is mean, and then it's median, and then it's mode. Mean median mode has its own merits and demerits, and we have already taken up that whenever your data is categorical, then we'll be making use of mode. We prefer making use of mode. If our data is skewed data, we prefer taking up median. And if our data is continuous or discrete, then we can take up mean for the analysis. Moving on to the measures of dispersion, we have, as the name suggests, the measure of dispersion shows the scattering of the data. It tells the variation of the data from one another and gives a clear idea about the distribution of the data. The measure of dispersion shows the homogeneity or heterogeneity of the distribution of the observations. The main idea about the measure of dispersion is to get to know how the data is spread over the x-axis and y-axis. It shows how much the data vary from their average value. So basically in statistics we can say there are two at most uh, important statistics. One is the mean, arithmetic mean or the average, and second is the variance, which is basically a measure of dispersion. Why these two are important? Because one is determining the central position and the other is determining the shape of the distribution. That is how spread your values are, how clustered your values are. So if your values are clustered enough, then we say that dispersion is less. However, if you have a value say ranging from 0 to 100 and we have a value ranging from 0 to 10, then definitely 0 to 10 is less spread as compared to 0 to 100. So measure of dispersion take into account that how much spread is there in the distribution, and as per the spread or as per the dispersion around mean majorly, we can comment on the standard error of mean, because standard error of mean is dependent on the population variance. So if a population is spread enough, that means our sampling distribution will be a distribution in which we'll be very far away from the population mean if we are taking up n to be very small number. So there are different measures of dispersion. Let's take up how the hierarchy of dispersion evolved. And the very first in this is range. So range is nothing but the difference between maximum and minimum. What is the maximum value in your data set? What is the minimum value in the data set? And dispersion simply gives the difference between the maximum value and the minimum value. So obviously it is simple to compute. So that is its merit. It is the simplest measure of dispersion. It is easy to calculate, it is easy to understand, and it is independent of change of origin. Whereas demerits is, it is based on two extreme observations. So whatever is happening in between these two observations is not creating impact on the dispersion. A range is definitely not a reliable measure of dispersion because it is only dependent on two extreme values and it is ignoring all the other values of the data. Then it is dependent on the change of scale. Obviously, if you are taking up 10 to 100 and you are taking up 200 to 300, then change of scale is changing the dispersion value or the range value. Then the next is quartile deviation. Quartile basically divides the data into quarters. The first quartile takes into account 25% of the values. Second, take into account 50% of the values of the data. And quartile 3 takes into account the 75% of the values in your data. So the first quartile that is given by Q1 is the middle number between the smallest and the median of the data. So first 25% of the data. The second quartile Q2 is the median of the data, that is 50% of the data. Third quartile Q3 is the middle number between the median and the largest number. So that means from end it is taking up 25%, or from beginning we are covering 75% of the data figures. So we have another measure of dispersion, is quartile deviation, and quartile deviation is Q3 minus Q1 by 2. So again, it has drawbacks and merits too. So the merits of quartile deviation are it uses half of the data, then it is independent of change of origin as of range. Then all the drawbacks of range are overcome by quartile deviation. That is, we were talking of that range is based on extreme values, etc. So that is now taken off. Then the demerits is it ignores 50% of the data. It is dependent on the change of scale, and again, it is not a reliable measure of dispersion. Then comes mean deviation. So, mean deviation is basically the deviation from the central value. Mean doesn't mean that it is mean or x bar, it can be median, it can be mode. So, mean deviation is basically nothing but the difference of a value from its computed central value. And when we take average of it, then that becomes mean deviation. So if we take up mean deviation from average, then it will be 1 upon n summation xi minus a, where a is the mean or average. For grouped frequency, definitely frequency will be multiplied and it will give the answer. Merits of mean deviation, it is based on all observations as we are taking up summation or average of xi minus the central value that we are taking into account. It provides a minimum value when the deviations are taken from the median independent of change of origin. Then it has demerit that it is not easily understandable. Its calculation too takes time, is dependent on change of scale, and ignore positive and negativity in the mathematical treatment because we are taking mode into account. So all these limitations are basically covered up in standard deviation. That is one of the most widely used measure of dispersion. And in this measure of dispersion, we are taking up the average of sum of squares of the deviation from the central value. Why we are taking up square? Because there are two reasons for that. First, square incorporates the underutilization and overutilization of a particular value from its mean. So if I have say mean as 20 and observation as 10 and one is 25. So me when we are squaring the difference, then it take into account equally the deviation. However, if the purpose of squaring is that it unintentionally add weight to our variance. For example, suppose one of my difference is coming out to be 0.1 and one difference is coming out to be 100. That is xi minus x bar is coming out to be zero point 0.1 and 1 xi minus x bar is coming out to be 100. So if we square up, then 100 will go 10,000 times. 100 will become 10,000 and zero point 0.1 will become 0.01. So basically we are saying that we are having more dispersion because of this wider difference. So if we have more wide ranges, squaring will definitely add on to those wide ranges or will actually exponentially rise those wide ranges. And as far as the formula is concerned, we have it is 1 upon n summation xi minus x bar whole square, or that is variance. So standard deviation will be square root of 1 upon n summation xi minus x bar whole square. So we have a standard deviation is the positive square root of the arithmetic mean of the squares of deviations of the given values from their arithmetic mean. It is denoted by Greek alphabet sigma, and it is also referred to as root mean square deviation. For grouped frequency distribution, variance formula is square root of summation fi into yi minus y bar divided by n, where n is summation fi. So then moving on to the merits and demerits of standard deviation. Obviously, it is more time consuming. It is not easy to calculate, it is difficult to understand by layman, and it is dependent on change of scale. However, the merits of standard deviation are: standard deviation is zero if all observations are constant, it is independent of change of origin, it is least affected by the fluctuations of the observations, it is done by squaring the deviations so that overcomes the drawback of ignoring signs in the mean deviation, then it is suitable for further mathematical treatment. Now, moving on to the normal distribution. Normal distribution, we can say, is like a God distribution in mathematics because almost any distribution can be approximated to normal distribution. So, normality is basically the symmetricity plus it has the advantage of getting converted into standard normal distribution, and its symmetricity, mean, median, mode, coinciding are some of the properties which make normal distribution one of the most wide distribution. So normal distribution, also known as Gaussian distribution, is a probability distribution that is symmetric about mean, showing that data near the mean is more frequently in occurrence than the data which is far from the mean. So the shape of normal distribution is a bell-shaped curve. A normal distribution is the proper term for a probability bell curve. In a normal distribution, the mean is 0, the standard deviation is 1. This holds true for standard normal variate. It has 0 skew and a kurtosis of 3. So normal distributions are symmetrical, but not symmetrical distributions are normal. So vice versa condition is not there. In reality, most pricing distributions are not perfectly normal, but they are within 1.95 limit of the normal distribution, and hence they can be approximated to normal distribution. Then this is the famous and most widely used observation that for a normal distribution, 68% of the observations are within plus minus 1 standard deviation, 95% are within plus minus 2 standard deviations, and 99.7 are within plus minus 3 standard deviations. So here is pictorial view of normal distribution. We have the first picture is representing the 68, 95, 99.7 rule, which we said just before this picture. Then we have skewness and kurtosis concept. So skewness basically represents the distortion in the symmetricity, whereas kurtosis represent how much curve is flattened or is reaching towards peak, etc. So that is kurtosis. Whereas skewness measures the symmetry, kurtosis measures the thickness. So skewness and kurtosis coefficients measure how different a given distribution is from a normal distribution. The skewness measures the symmetry of a distribution. The normal distribution is symmetric and has a skewness of 0. So if the distribution of data has a skewness less than 0 or greater than 0, then to some extent it can be treated as normal approaching. But if the number is too high or too low, then accordingly, if the skewness is less than 0, then that becomes a negative skewed curve. And if skewness is greater than 0, then that becomes a positive skewed curve. Positive skewed curve has right tail of the distribution longer, whereas the negative skewness has left tail of the distribution longer as compared to the right tail. Coming on to kurtosis. Kurtosis statistic measures the thickness of the tail ends of a distribution in relation to the tail of normal distribution. Distribution with large kurtosis exhibit tail data exceeding the tails of the normal distribution, that is 5 or more standard deviation from the mean. Distributions with low kurtosis exhibit tail data that is generally less extreme than the tails of the normal distribution. So a normal distribution is mesokurtic. So anything which is not mesokurtic is either leptokurtic or platykurtic. So the normal distribution has a kurtosis of 3, which indicates that distribution is neither fat nor thin. So if an observed distribution has a kurtosis greater than 3, then that means it has heavy tails when compared to normal distribution. And if the distribution has kurtosis of less than 3, then we say it has thin tails when compared to normal distribution. So we have the blue curve in this is platykurtic. Platykurtic has more spread. Then we have leptokurtic. Leptokurtic is thinner at the mean, whereas the green curve is normal, standard normal distribution, which is mesokurtic. Now, one of the most wide applications of normal distribution is the z-score or z-score. The number of standard deviation from the mean is called as standard score, sigma, or z-score. So, to convert a value into standard score, we just need three values. We need x, which follows normal distribution, we need mean, and we need the sigma. Sigma is the standardizing agent. So, first subtract the mean, then divide by standard deviation, and then doing this is called as standardizing the things. So, the z square formula is given by x minus mu upon sigma. This is the z score or a score, or this is called as standard score. X is the value to be standardized, mu is the mean of the population, and sigma is the population standard deviation. So this was all about uh, normal distribution, how to convert normal distribution into standard normal distribution. Just giving a quick concept of correlation and regression. So correlation is definitely the relationship between two variables. So if we take into account statistics, then it determines that if one value is increasing, then the dependent value is increasing or decreasing. So when we have that x and y, if our two variables in such a way that x and y have a direct and perfect relationship with each other, then the correlation coefficient turns out to be 1. So that means if one is increasing, the other is increasing by 1 unit. And if there is negative correlation, perfect negative correlation, then if one is increasing by 1 unit, the other variable will decrease by 1 unit. So the word correlation is used in everyday life to denote some forms of association. In statistical terms, we can use correlation to analyze and to denote the association between two quantitative variables. We also assume that the association is linear, that one variable increases or decreases with a fixed amount or a unit increase or decrease in the other. The other technique that is most often used in these circumstances is regression, which involves estimating the best straight line to summarize the association. So correlation gives the magnitude, whereas the exact relationship is given by the regression coefficients. Then correlation coefficient is measured on a scale that varies from +1 through 0 to -1. Complete correlation between two variables is expressed by either +1 or -1, which is also called as perfect positive and perfect negative correlation. When one variable increases as the other increases, then the correlation is positive. When one decreases as other increases, then it is negative. And when the relationship is random or there is complete absence of relationship, then we say that correlation is zero or the two variables are not related with each other. Now, this is the graphical representation. Figure A represents that there is perfect positive correlation because if A is increasing by 1 unit, or if x-axis is increasing by 1 unit, then there is increment in y-axis by 1 unit. B is similar, but instead of perfect positive correlation, we have now negative correlation. C is the case wherein there is no relationship, the pattern is random, and D is non-linear relationship. So we compute Pearson correlation coefficient, and which is given by R, and the formula for computing R is summation xi minus x bar into yi minus y bar. That is how the two are related, divided by summation xi minus x bar whole square into yi minus y bar whole square in under root form. So correlation is also called as covariance of xy divided by sigma x into sigma y. So how the two variables are related, that comes in covariance, and then we are normalizing or standardizing it using sigmas. So we are dividing it with sigma x and sigma y. For positive Pearson R correlation, both variables should be normally distributed, and this holds true for negative or zero correlation too. Other assumptions include linearity and homoscedasticity. Linearity assumes a straight line relationship between each of the two variables, and homoscedasticity assumes that data is equally distributed about the regression line. Moving on to the concept of regression, as said, regression can give an exact equation, thereby giving the rate of change of one variable, that is independent variable, to dependent variable. So correlation describes the strength of an association between two variables and is completely symmetrical. The correlation between x and y is the same as the correlation between y and x. However, if the two variables are related with each other by a certain amount, the other change on an average by a certain amount. If y represents the dependent variable and x the independent variable, then the relationship is described by y on x, regression equation of y on x. The relationship can be represented by a simple equation of the form y is equal to a plus bx plus epsilon. A is basically the constant or the fixed cost, if we can say up in terms of cost. B is the rate of change. X is the independent variable and epsilon is the unexplained error or the residual. So we have the equation is given by y is equal to a plus bx plus epsilon, where y is dependent variable, x is independent variable, a is intercept, b is slope, and epsilon is error. When we talk of regression, then there are two measures which indicates whether our fit is good enough or not. One is called as R square and one is called as MSE. So R square is a measure of association. It represents the percent of the variance in the values of y that can be explained by knowing the value of x. So if we know x and we are knowing it y, then it is basically how good your fit is. R square usually varies from 0 to plus 1. 0 means that none of the variance is being explained, and 1 means that most of the variances is being taken into account. Then we have that residual can be considered as an estimate of true error term. So these are the assumptions of regression, that is linear regression. Both the independent and dependent variable are measured at the interval or ratio level. Remember, we cannot take it on ordinal data and categorical data or nominal data. So for nominal data, we have the chi-square test of association, which indicates whether two variables are independent or dependent. So majorly for ordinal data or nominal data, we have chi-square test of association. Otherwise, we have regression. So the variables of regression are measured at the interval or ratio level. The relationship between independent and the dependent variable is linear. Error in prediction of y are distributed in a way that approaches the normal curve. Error in prediction of y are all independent of one another. Then the distribution of the errors in prediction of the value of y is constant regardless of the value of x. So these are the assumptions of regression. Usually in modeling paper, we employ the technique of regression modeling. We have now advanced methods of regression, econometrics method mainly. But in research methodology, we do have regression, but simple regression and multiple regressions. So let us begin hypothesis testing. Now, when we talk of hypothesis testing, then we should keep in mind that we are talking of inferential statistics and not the descriptive statistics. So, to take up the concept, we have statistic is basically divided into two branches. One is called as descriptive statistics and another is called as inferential statistics. When we are dealing with business research, then in research methodology, we take up the concept of inferential statistics, wherein from the sample information we verify whether the statement on a particular population parameter is not to be rejected or to be rejected. So, do keep in mind that hypothesis testing caters to the inferential statistics part. Now, the concept of hypothesis testing states that there are two types of hypothesis. One is called as null hypothesis and another is called as alternative hypothesis. H0 is null hypothesis and H1 is alternative hypothesis. Now, what is the concept of null hypothesis and alternative hypothesis? Basically, these two are mutually independent cases, and suppose we need to test that the mean of the population is say mu naught or not, then in that case the null hypothesis will be the sample statistic does not differ significantly from the hypothetical parameter value, and in that case of hypothesis H naught will be the sample statistic do not differ significantly. So that is, suppose I want to address to the issue that whether my population mean is say a particular quantity, say mu naught, or my population mean is not mu naught. Then in this case we take up null hypothesis as mu is equal to mu naught and alternative hypothesis as mu is not equal to mu naught. Do keep in mind that the hypothesis testing takes into account white and black concept. For that, there is no gray region. So that means it says that either we should not reject H naught or we should reject H naught. There is no middle way, and that is why we take up that H naught and H1 should complement each other. So, when we talk of hypothesis testing, therein we talk of one tail hypothesis testing and two tail hypothesis testing. Now, what is one tail hypothesis testing? One tail hypothesis testing is the case wherein we are suppose taking up whether we need to find that the mean score of the student is 50 or H1 mean score of the students are less than 50. Then this is the case wherein we are just taking up or we are concerned whether the focus region is 50 or less than 50. So that means if it is 50 or more, then that is favorable to me. However, if the students are scoring less than 50, so that means that is not favorable to me. So there is some performance issues with the students or with the learning. So in order to assess this, we need to take up this. Now, if we take up this as it is, then this has one limitation or flaw, I would say. That flaw is that it is not covering all the cases that needs to be addressed. So, to make it a universal case or to make it a universe, we will put up greater than sign over here. So that means now if my mean is coming out to be greater than or equal to 50, then that is in favoring of H naught. Otherwise, if mu is less than 50, then it is not in favor of H naught. Or we say that sample do not provide enough evidence to not to reject H naught or to reject H naught. Now, after taking up these basic concepts, we have the concept of errors in hypothesis testing, and the errors in hypothesis testing are called as type 1 error and type 2 error. So what is type 1 error and type 2 error? Type 1 error is basically reject it's not when it is true. And type 2 error is basically accept H naught when it is wrong. That is, accept H naught when H1 is true. So we say that this is accept H naught when it is wrong. Type 1 error is denoted by alpha, and this is called as level of significance. Type 2 error is denoted by beta. We have 1 minus beta indicating the power of test. Now let us first have a quick look on what type 1 and type 2 error suggests. So this can be taken up by a very simple example. Type 1 error is also called as producer risk. That is, type 1 error is probability of rejecting a good lot. Rejecting a good lot. So this is called as type 1 error. And what is type 2 error? Type 2 error is probability of accepting a bad lot. So this is beta. This is called as producer risk. And this is called as consumer risk. Now let's take up what is producer risk and what is consumer risk. So take a very simple case. Suppose you have box of apple and those box of apples contain 95 good apples and 5 are rotten apples. Now suppose a customer comes and he randomly pick up 3 elements or 3 apples from that box, and by chance it happened that all the 3 apples that came up in the hand of customer were rotten, rest 95 were good. So in that case, the consumer will reject a good lot, right? Although the lot was good, but it happened that out of 5, all the 3 apples landed in the hand of consumer. So such type of error is basically called as producer risk, while consumer risk is the reverse case. That is, now out of 100, 95 are rotten and 5 are fine. But consumer happened to pick up those 5 not rotten apple but perfectly fine apple. So he'll be accepting a bad lot, otherwise which was not consisting of good apples. So this is called as consumer risk. Now when we do hypothesis testing, then what matters to us is alpha. So we always keep up alpha to a set standard and then we conduct the hypothesis testing. And basically, if I would say that a number or sample size is dependent on what we take up as the standard deviation or the error that we want to have in our analysis. So this is the initial basic of hypothesis testing. One thing more to consider, and that is there is lot of confusion in how to take up H0 and H1. So for that there is simple one rule. H0 is taken as the hypothesis of no assumption. That is to say, H0 is a neutral case. So suppose take it like this. We have say old machine and new machine. Now what hypothesis testing will take into consideration? Hypothesis testing will take into consideration in H0 as unbiased opinion, and that unbiased opinion will be the output from machine A, that is old machine, will be same as the output from new machine, that is machine B. And alternative hypothesis will be the output from machine B is greater than the output from machine A. So in this way we make up H0 and H1. Then another point worth considering in hypothesis testing is we always compute hypothesis testing under the condition that H naught is true unless and until we get a sample which is so extreme that it is lying in the rejection zone. And that rejection zone is basically determined by the alpha which we are taking. So, to represent it in a pictorial manner, we are taking up normal distribution for the time's sake to represent the general case. So, we have this as the normal distribution, and we have this entire takes into account the mu case, wherein we are saying that H naught is true. This entire x-axis represent that H naught is true until and unless we are committing alpha by 2 error over here and alpha by 2 error over here. So this is the zone where we'll be rejecting H naught. So if I would say this is the zone, this is the zone where we do not reject H naught, and in case of two-tailed test, this is the zone where we reject H naught. Now, if this would have been a two-tailed test, then how we go about it? Sorry, if the test would have been one-tailed test, then how the graph would appear? So suppose our H naught is mu is less than equal to 50 and H1 is mu is greater than 50. Then in that case, we'll have this as a rejection zone and we'll have this as a do not reject zone. So that means if my computed statistic of mu, which is ultimately converted to standardized form of Z, if my calculated statistic is lying in this region, then we say that sample is not providing enough evidence to accept H naught. And if my sample statistic is lying in this region, then we say that do not reject H naught as per the sample. Or we say that sample do not give significant evidence to reject H naught. So this is the case wherein we are taking up H naught is say mu is less than equal to mu naught and H1 is mu is greater than mu naught. Now if it would have been the reverse case, then that is like this. Then this would have been alpha. So this is one tail test. So this would be do not reject zone and this would be rejection zone. So we'll be having H naught in this case as mu is greater than equal to mu naught and H1 is mu is less than mu. Now if we want to be statistically correct, then we do not conclude our hypothesis that we are accepting H naught. Why so? Because accepting H naught means that it is making our statement a universal statement. But do take into consideration that hypothesis is not a universal statement. Hypothesis does not give a law. Hypothesis is there to justify whether this holds or not as per the sample information. So be very careful when you are concluding the interpretation statistically, we say reject H naught and do not reject H naught. So better it is to say that this is do not reject zone and this is reject zone rather than saying that accept H naught and reject H naught. So this is getting deep into statistical terms. So this zone is do not reject zone and this zone is reject zone. I'm not saying this as accept zone. Casually, we take up this as accepting zone, but statistically, it is do not reject zone. Then, one more point to take into consideration is there is not the relationship that alpha plus beta is equal to 1. That is, level of significance and type 2 error sum is not equal to 1. So, do take into consideration that alpha plus beta do not obey by the hardcore rule that the sum is equal to 1. Let me take up one more concept, and that concept is the concept of statistic versus parameter. Now, what is the difference between statistic and parameter? Statistic is basically computed from the sample, whereas parameter is the value of the hypothesis that we need to assess. Practically, we can calculate statistic, but we cannot calculate parameter. Parameter can be taken as set standards. For example, we have suppose a cold drink bottle needs to be filled by 750 ml. So, in that case, we say we have a set standard of mu is equal to 750 ml. So, this 750 ml is usually the set standards, whereas when we talk of statistic, then corresponding to mu will be taking up x bar. So what we can do in this case is we can randomly take up, say, Coca-Cola for we can randomly pick up 24 bottles and take the average, and then we can compute whether the average filling in that Coca-Cola bottle is 750 or 770 or so. So this x bar is summation xi by n, where n is your sample size. Whereas if we are taking into consideration parameter, then mathematically this formula will be summation xi by capital N, where capital N is the population size. So, do not get confused between statistic and parameter. I would say inferential hypothesis testing is rather a journey from statistic to parameter. We'll be computing up statistic, and on the basis of that calculated statistic, we'll be commenting on the parameter of the population. Now, when we are considering when we are considering the hypothesis testing, then we have that hypothesis testing can be classified into parametric test and non-parametric test. Now, when we are commenting something on the parameter, like we were saying, whether the population mean is 50, whether the population variance is 100 or not, then such kind of testing is called as non-parametric testing. Sorry, then such kind of testing is called as parametric testing. However, when we are testing, say, the relationship between two variables, and those two variables are related in terms of independency or dependency. That is, we are talking of, say, chi-square test of association, wherein we want to identify whether the demographic is related to the opinion that we are talking of or not, then in that case, we are not commenting or we are not analyzing a population parameter. We are simply saying whether there is the relationship between the two parameters or the two characteristics or the two attitudes that we are taking into consideration. So, in research methodology, we may use a parametric testing, we may take up non parametric testing depending on the availability of data. Wherein I would say, suppose Likert scale is there, then in that Likert scale, we go for non parametric test. However, if we have quantitative data, suppose we need to find whether the average height, we are taking up height of the children in a questionnaire, and we need to find whether the average height of student is mu naught or not, then in that case we'll employ parametric test. So these are some quick concepts related to hypothesis testing. We'll be taking up one by one cases in hypothesis testing, and then we'll move on to ANOVA, which takes into account the comparison of means of multiple population. But before that, we'll take up certain examples of how to test about population mean, how to test about population variance. Then we'll consider the applications of chi-square test, that is test of association. Then we'll take up ANOVA. So this is how we'll be proceeding in the lecture, keeping in mind these concepts of hypothesis testing.